Alright, good morning, good afternoon, good evening class. This is Mr. Arocena, and on today's video we're going to be talking about electric current. So moving off from electrostatics, and we're going to move into non-static electricity. So what is electric current? Electric current is basically the opposite of static electricity, I guess, because static electricity was non-moving charges. So like if this was an object and you had it charged, then the negative charges, or negative charges, because positive charges don't move, the charges would basically stay on your object and they don't move. Whereas in current electricity, we have moving charges, or basically moving negative charges. So if we have a negative charge, this negative charge has the ability to move through the substance. Something is causing these negative charges to move. So just to be clear, like in static electricity, the only thing that moves from objects to other objects are electrons. So in current electricity, the only charges that really move are electrons. Although I guess if you had mobile protons, like in the form of hydrogen ions, then you could consider that a moving charge as well if the hydrogen ions were moving. All right. So that's kind of the difference between static electricity and current electricity. Static electricity, your charges stand still. Current electricity, your charges move. Now current, we measure the amount of current that moves. We measure that in a unit called amperes or amps. It's usually the abbreviation is just amps. And this is characterized basically as, I mentioned here, a flow of charges. So it's basically moving charges that move through. It's handy to think of it as a flow because electrons, or I guess charges in a current, move very similarly to how water moves through a hose. And we'll probably use that analogy later on. The symbol for current in electricity is I, and the amp, by definition, is charge per second. So current is charge per second that passes through a certain point. Now, interestingly enough, the current depends directly on your potential difference, otherwise known as voltage. Because if you remember, voltage was the amount of energy per charge. And basically, the more voltage you have, the more current you can create, because the charges will have more energy. So you can think of it as the charges can move faster because they have more energy. The charges move, and as you get more of these charges moving, you have more flow of electricity, okay, more flow of current. All right, now in addition to electrons, or I guess electricity, flowing electricity, there is something that can prevent the flow of electricity, and that's what's called resistance. So resistance is a property of matter that prevents the flow of current. So Georg Ohm, discovered this relationship where current is inversely dependent on the resistance. Basically, it means that the more resistance you have, the less current exists in the circuit. And the reverse is also true. If you have less resistance leads to greater current. And kind of makes sense, because it's like if you're, if you go back to the hose analogy, if your hose has a blockage, that's a lot of resistance, so the flow of water is reduced. But if you don't have a blockage, there's no resistance or very little resistance, so the flow of water goes down just fine. So resistance will impede the flow of current. That's not to say resistance will stop current, although if the resistance is high enough, current will be reduced to basically zero. But in general, resistance will just slow down or impede the flow of current. But like I said, if the resistance is high enough, then the current will be reduced to a very negligible value. Okay, so if you remember from static electricity, insulators have generally very high resistance, because insulators prevent the flow of electrons, have high resistance, and conductors are the opposite, where they have low resistance. And then the semi-metals, or the metalloid substances, semiconductors, I guess, they have, they're somewhere in between, where they're not fully conductive, but they're not fully insulative either. So they have the ability to allow some current to go through, but not all current. Okay. Now, Georg Ohm, during his study of electricity, came up with the following relationships regarding current electricity. And we basically talked about it earlier. We'll just not put them in mathematical terms. He noticed that current was directly related to voltage. So current and voltage are directly related. More voltage, more current. Less voltage, less current. And he noticed that this relationship was also true, where the amount of current is inversely dependent on the resistance. So more resistance, less current, less resistance, more current. And he put the two together to get the following. And this is what's known as Ohm's Law. Some of you may remember this from Science 9, because we first introduced it to everybody in Science 9, and I think most people were like, why is there math and science? And that's, depending on your teacher, would have told you that math and science go hand in hand, and if you're, since you're taking physics, you know that very well. So Ohm's Law, we can rearrange this to get other relationships. The usual form of Ohm's Law is given by this relation, this equation, V equals IR. This one's easy to remember because you just remember it as VIR, V-I-R. And then the other one was R equals V over I. So in Science 9, these were the three equations you would have learned regarding Ohm's Law. And it's interesting because unlike the other relationships we studied recently, like force of gravity and electrostatic force, there's no random constant. It just happens that, yeah, current, voltage, and resistance are related this way without the need of some kind of external constant. Okay. There you go. That's Ohm's Law. Ohm's Law is very handy for a lot of things. Anything electricity related, you are probably going to do, you're going to do some kind of Ohm's Law calculation. And whether you are building some kind of small scale electronic for like RC cars or other small scale electronics, Ohm's Law will probably be factored in there somewhere. Or if you're building larger devices, Ohm's Law will be necessary for calculating a lot of things. Now, with regards to electrical current, this is a rather confusing thing with regards to direction of current, because we have, in physics, two different definitions of current. And in electronics work, we have one definition, which is actually incorrect. So in physics, our two definitions are as follows. We have electron flow as one type of current, and then we have conventional current as the other type of current. So electron flow describes the direction of electron travel. So direction of electrons generally go from a negative to a positive. So if I have a battery and there's a positive end and a negative end, the electrons will flow in this direction. Okay, so that's electron flow. Conventional current, however, is the opposite, because for the longest time, when electricity was first discovered, I think it was Thomas Edison, he described the flow of electrons, or not flow of electrons, flow of electricity as going from the positive charge, or the positive end, to the negative end. So for the longest time, people who studied electricity had this idea that current flows positive to negative. And actually a lot of, I want to say, electrical circuit construction uses this definition of current when creating their circuit diagrams and their devices, which is, like I said, incorrect, because only electrons move. Protons do not move in an electrical circuit, only electrons do. So electron flow is the more correct way to look at an electrical current, but if you're in any kind, if you become an electrician, conventional current is the one you're going to see more often, because, like I said, for the longest time, early electricians thought that positive charges moved, not negative. Then we learned more stuff and eventually realized we were wrong. All right. So keep that in mind. In chemistry, we will probably also talk about this, but in chemistry, we limit ourselves to electron flow in chemistry. That's all chemistry is, just electron flow. All right, let's go through some examples of how to work with our new equations. All right, example 1. What is the current in the conductor if 2 coulombs of charge flows through a point every 15 seconds? So this equation will use the fact that current is the amount of charge per second. Or I guess I should use T for that. Okay, so we'll use T. Time. There you go, T. All right, so the amount of current will be the amount of charge. So we say 2 coulombs of charge flowing through a point in 15 seconds. So the current at this point will be 2 divided by 15 is not 7.5. That's 15 divided by 0.13. 0.133. That is 0.13 amps. There we go. The current you can calculate this way as charge per time or charge per second. All right, next example. Here we're asked what is the resistance in a conductor if there is a potential difference of 5 volts and the current is 2.5 amps. So here's an application of Ohm's Law. So I'll write out Ohm's Law. Again, this is the easiest version of Ohm's Law to remember because it's relatively straightforward, at least for me. You could remember all 3 versions if you really felt like it. So we're asked to find what is the resistance. So rearranging this equation, we get the following. Resistance is V over I. We have a potential difference of 5 volts. Remember, potential difference and voltage are the same. We have a current of 2.5 amps. And doing this calculation, 5 divided by 2.5, this will give me a resistance of 2.0 ohms. So Ohm's Law is relatively easy to work with because it's the equation is not too bad compared to some of the other equations we've done in physics. All right, example 3. How long would it take a total charge of 12.5 coulombs to pass a point in a conductor if the current was 7.5 amps? So this one's worded slightly differently. So we want to figure out the amount of time. Here we're going to use our definition of current. So current is going to be charge per time, charge per second, and we want to figure out the amount of time it takes for this much charge at this much current. So we'll rearrange this equation to find time. Time will be charge over current. So we have a total of 12.5 coulombs of charge, current of 7.5 amps, and this will give me 12.5 divided by 7.5, a total time of 1.7 seconds. 1.7 seconds. 7.5 amps is actually quite a lot of current, and passing this amount of charge in 1.7 seconds is quite a lot. To put things in perspective, I believe, like if you're looking for fatal currents, you only need about 0.2 amps passed between the arms of a person to stop their heart, I think. Yeah. So you don't need that much current. Like this much current will be really, really high. There are some applications though where having that much current is actually useful. It's quite dangerous. Anyway, so there's Ohm's Law. Hopefully it's a review of what we learned in Science 9. We'll be using Ohm's Law quite a bit throughout this unit in combination with some other rules or some other equations. All right, your assignment then for this lesson will be as follows in your textbook. It's actually 2. So there we go. If you have any questions, you guys all know how to contact me.